Lab 2 Projectile Motion. The purpose of this lab was to observe the motion of an object in projectile motion. The main principle we were trying to observe was Newton's second law. Newton's second law states the change in motion is proportional to the forces acting on an object. Models. Series 1, the blue, is the observed x versus y position. Series 2 is our predicted without drag force, and Series 3 is the predicted with drag force. Here we can see a brief preview that all the graphs have a parabolic curve to their motion. The system is the paper ball, and surroundings is gravity, drag, and the person that threw the paper ball. Initial conditions. For throwing our paper ball, our position vector was 0 in the x, 0.631 meters in the y, and 0 in the z. The initial velocity was a toss given to the paper ball. It was 1.45 meters per second in the x, 2.127 meters per second in the y, and 0 in the z. I took the average across the whole time interval to get the average velocity for the vi in the x direction, and then only for the first few points for the vi in the y direction, because velocity for y isn't constant the whole time like the x directions is. The mass of the paper ball was about 0.005 kilograms. To start off our experiment, we started by one of my lab partners throwing the paper ball while we had a meter stick. Then we uploaded the video to the tracker app. We used the meter stick we had in the background to set the tracker video to scale. We set x plus in the right direction and y plus in the upwards direction. We set the axis origin to be 0 in the x direction where the ball was thrown from, and 0 in the y direction to be on the floor. So the initial y wasn't at the origin. Then we used a tracker to get our observed data points. Then we calculated initial positions and velocity like talked about before and uploaded those conditions to our GLOW script code. Then our GLOW script code gave us back our predicted x versus y position graphs, both for without drag force and with drag force. Then I used this data to make my model, and the ball wasn't thrown in the video until about the 0.3 mark we can see here, so ignore the data on the graphs until then. First, for my code, I input the mass of the paper ball to 0.005 kilograms. Then, like talked about earlier, I input the initial position and velocity. Then I input t initial to be t equals 0 seconds. Then delta t to be 0.03 seconds. That was an average. And then I would loop until 1 second since that's how long our video was. F net equals F of gravity plus F of drag. So to get my non-drag force graph, I just input the initial value of b equals 0 in my equations to be able to get the constant b, which is the drag force constant. And the force of gravity is only in the y direction, which is negative mass times gravity. And then the force is only in the y, which is that negative b constant times the magnitude of the velocity. Then I made arrows pointing in the direction of F gravity, F drag, and the ball position. Then using my computational model with drag and comparing it to be my observed graph, I got the drag constant b equals 0.001. Then using this data, I made my updated computational model with the force of drag included by inputting all three sets of data into Excel. Differences and similarities. As we can see here, the computational models are similar in the beginning of the model to the observed data, and then strays away in the end. We can see that they are all curved parabolic shapes which demonstrate the projectile motion. These similarities demonstrate Newton's second law. Because of Newton's second law, we can see here that all three forces, the throw force, the force of gravity, and the drag force, give the motion that parabolic shape. Some reasons for errors and differences between the graphs are human error, and also my estimation for drag force could be off. Additional questions. So what does this mean? So our computational graph with only gravity doesn't have terminal velocity because it has a constant velocity and thus a zero net force, while our computational model with drag does have a terminal velocity because it is parabolic and not a linear relationship, which indicates a change in velocity throughout time and thus a non-zero net force. What if? The ball was thrown straight up with the same initial velocity. If the ball was thrown straight up, we only have to account for the magnitude of the velocity in the y direction, as opposed to our experiment that also put some of the velocity into the x direction as well as the y direction, as we can see here in this equation. So in this case, our experiment throw would touch the floor first because the one thrown straight up will have all the velocity used to go up in the y direction, while ours will use part of it to go sideways in the x direction instead, so it won't go as high in the y direction and thus won't have as much to need to travel back down. Thank you.